We present CLoSD, a text-driven character controller performing multiple tasks through on-the-fly diffusion guidance. CLoSD is given a text prompt and a target location of a body joint. Together, these serve as a useful description for a variety of tasks. As a result, a single CLoSD controller can perform a sequence of different tasks. CLoSD generates diverse and versatile motion on an SMPL-compatible robot, which is interchangeable with the SMPL mesh. As well understood in recent literature, action controllers greatly benefit from kinematic examples. However, they typically rely on a small set of examples and are unable to scale to large datasets and multiple tasks. Our key insight is that motion diffusion can generate plans in real time for a tracking controller, flexibly guiding it to various tasks. But diffusion models are slow and unaware of the physical world, and at the same time, tracking controllers are not trained for generation-related inaccuracies. To overcome these challenges, we designed CLoSD, which maintains closed-loop interaction between a real-time diffusion model and a robust tracking controller. Our real-time diffusion planner, DIP, rapidly generates short-term sequences according to the inputs and previous motion autoregressively. The tracking controller is an RL policy that consumes the DIP motion plan frame by frame and creates the actions to track it. After following the plan, we close the loop by feeding the frames performed in practice back into DIP as the new prefix. Depicted here is a sitting down motion performed by CLoSD. Therefore, getting up from the sofa is as easy as changing the prompt and target in mid-simulation. Here, the blue markers depict the diffusion plan for the final performance in orange. Note how the controller corrects micro-artifacts of the diffusion planner. Let's look at some results. As already shown, CLoSD performs goal-reaching in a physical simulation. But there are many ways to reach a target location. By simply changing the text prompt, we can reach the target with any desired type of locomotion. For example, jogging, jumping, using big diagonal steps, and even dancing. CLoSD also performs striking. The striking, again, can be controlled through the text prompt and corresponding targets, which could be both hands, a foot, or a wrist, as seen in current examples. And since CLoSD is a single model, these tasks can be natively combined into a sequence. We compare our work with UniHSI, which is a state-of-the-art multitask controller. UniHSI indeed reaches contact points, but is not aware of the motion semantics, and hence touches the target, for example, instead of punching it. When asked to get up, UniHSI settles for bending the pelvis to minimize the distance to the target. In CLoSD, the semantic understanding of the diffusion model enables performing these tasks correctly. We compare CLoSD to two baselines, an open loop without replanning or feedback, and a closed loop without fine-tuning the components to communicate with each other. As can be seen, only the full closed system with semantic guidance and object interaction reasoning produces natural human motion for sitting down and getting up. Our statistical success rate evaluation over 1,000 episodes further exposes the merits of CLoSD. For more details, please refer to the paper. Thank you for your time. Case closed.